Good day, grade 12 learners. Welcome to today's technical science lesson. My name is Musa Zulu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Right, today, grade 12, our knowledge area is again mechanics as last week, and the topics Newton's laws and momentum. You'd remember that last week we looked at Newton's first law of motion and Newton's second law of motion. So our specific law that we're going to focus on for today would be Newton's third law of motion. Then we're going to look at a little bit of the momentum. We're going to be introducing momentum there. Right. Remember grade 12, during the lesson or even after the lesson, you can communicate with us, ask questions, share your thoughts on the lesson on our WhatsApp number 079 578 2908. Right. We'll again go through this paper structure because it's important that we understand that which topic with the topic we are doing, it comes from which paper and the structure of that paper. So our topic for today comes from paper 1 again. The structure of paper 1 is divided into two sections, like we said last week. That will be section A with 10 multiple choice questions most of the time. Sometimes you'll find that it has matching items, which is column A and column B. And section it's out of 20 marks, section A, and then you also have section B with structured or long questions that will add up to 130 marks or 122 if we have matching items back in section A. The total of the question paper is 150 marks and the duration of the paper is 3 hours. Right, so today our formula focus, the formulas that we are going to focus on are found there on your data sheet in table 2 there. And our focus today is going to be these following forces. The momentum formula, P is equals to mv, and the change in momentum formula, delta P is equals to mvf minus mvi. That's going to be the formulas that we are going to be focusing on today. We will try to understand what do they mean and how can we use them to answer questions. Right, as we have said, our focus in Newton's laws today is going to be Newton's third law of motion. So what I want us to be able to do by the end of the lesson with regards to Newton's third law of motion, first we must be able to state it. As all the other laws, it's important that we are able to state the law. And how do we state the law? The law must be stated according to our exam guideline. If each and every one of us should have an exam guideline in hand, and we should always be reading this exam guideline. So the law is stated as follows in our exam guideline. It says, when object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A. I'll repeat again. When object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A. Now, when you read the statement, it doesn't make much sense. You can't even understand what the statement is saying. So that's what we're going to be going through, trying to understand and break down this whole statement that when object A is exerting a force on object B is simultaneously exerts an oppositely directed force of equal magnitude on object A. However, I'm going to need you to be able to identify what we call action-reaction pairs. We must be able, after learning about Newton's third law, to identify what we call action-reaction pairs. Then you should be able to list the properties of action-reaction pairs for better understanding as well. Right. So, to understand Newton's third law, I want to try and ask a question here to say, let's say you have a person here and the person is on roller skates. So on skates there, and then the person decides to push against the wall. What is going to happen to the person? I'm sure all of us would agree that the guy that is pushing against the wall here is going to move. After pushing against the wall, the guy is going to move in the opposite direction where he was pushing. So if, let's say, the guy is pushing to the right, the guy will then move to the left in the opposite direction. So then the question should arise to say, what causes the guy to move? Because the guy is the one that is pushing the wall. The guy pushes the wall and he pushes the wall in this direction. Yet the guy moves in the opposite direction. It's not the wall that is moving, it's the guy that is moving. But it was the guy that was exerting the force on the wall. How does this happen? Well, Newton's third law gives us an explanation, and it gives us an understanding of how this comes about. So, what Newton tells us in his third law is that when this person here exerts a force on the wall, right, the wall will also exert a force on the person. So, what causes the person to move according to Newton's third law is the force that is exerted by the wall on the person. So Newton's third law tells us that every time an object exerts a force on another object, the other object will also exert the same force. So of equal magnitude, it must be equal in terms of size, but it will be in the opposite direction. This is the reason why the guy pushing against the wall moves in the opposite direction. So the guy starts by applying a force on the wall, right? And then the wall will also apply the force on the guy. And the force that is exerted by the wall on the guy is the same as the force that is exerted by the guy on the wall. They are the same in terms of their size, in terms of their magnitude. So what do we mean when we say in terms of their size? We mean if this guy exerts a force of 50 newtons, for example, on the wall will also exert a force of 50 newtons on the guy. That's what Newton tells us. He tells us that the forces are going to be the same. The only different thing about the two forces is that they will now act in opposite direction, which is the reason why now the guy tends to move in the opposite direction, because now he's being exerted on by a force of 50 newtons in that opposite direction that comes from the wall. However, he was the one that exerted the force first on the wall. So every time when you have an object A, we will call the wall our object A, right? And you have the person object A and the wall object B. So every time you have object A exerting a force on object B will simultaneously at the same time exert a force of equal magnitude in the opposite direction on object A. So these two forces are the same, they are in opposite direction. That's all Newton tells us. And this happens all the time. It doesn't matter the sizes of the object and which object are we talking about. As long as we have two objects and one object exerts a force on the other, the expectation is that the force that is exerted by object A on object B will be the same as the force that is exerted by object B on object A, but they will be in opposite direction. Right, as we continue, right, with Newton's third law of motion, these forces are usually referred to as action-reaction pairs, right? So we have two parts here, action-reaction, and we have pairs. The pairs indicates to us that these forces are always going to go in two, right? They are always going to go in two because there is one reacting to the other. There are always going to be two forces, the action force, and there will always be what? A reaction force. So they always go in pairs. So that's why they are called action-reaction pairs. Now, I have to say, grade 12, that I do not like these action-reaction pairs, even though I do not have any power to do anything about it, but I don't like the action-reaction pairs because sometimes it creates misconception in understanding the law. When we say action-reaction pair, we are not talking that there will be a force, right? And then after some time, there's going to be a reaction. Because when we say action-reaction pairs in general English, it sounds like there will be one thing, and then after some time, there will be another. That's the reaction. In this case, in Newton's third law, that is not what is happening. We are not having a force acting, and then after some time, we are having another force reacting. That's not what is happening. So that's what I want us to be careful about when it comes to this word here, action-reaction. When we talk about action-reaction pairs in Newton's third law, the two forces are occurring simultaneously. So there is no time in between where you are going to have one force acting, and then another force acting after maybe some seconds, exactly at the same time. That's why we have simultaneously. These forces are acting simultaneously. The moment force A or object A exerts a force on object B, at that exact moment, object B will be exerting a force on object A, and that force will be of equal magnitude and it will be in opposite direction. Here's our example. If we are having here a book resting on top of the table, we are going to have the force that is exerted by, so we are going to have the force that is exerted, the table, book exerted by the table. So we're going to have the force on the book, and that force is exerted by the what? The table, right? And you are also going to have a reaction force here. We are also going to have a reaction force which is going to be acting on the table, and it will be by the book. So it's force table by the book. These two forces are equal to each other, but they are in opposite direction, right? Here's another example. If you are seated down on a chair, right? When you sit down on a chair, your action force is the force that you exert on the chair. That's the action, right? Then there's going to be a reaction force, which will be the force exerted by the chair on you, the person who's sitting on the chair. But then remember, again, I want to emphasize, these forces are acting at the same time. There is no minutes or seconds in between where one action force occurs and the reaction occurs after. They occur simultaneously, exactly at the same time. I need people to have that to avoid misconception of thinking that I will have force A and then after some time I will have force B, because in general English, action-reaction pairs, it will sound like that. But that's not what we mean when we come to Newton's third law of motion. We mean exactly at the same time, you are going to have force A being object A exerting a force on object B. Exactly at the same time, object B will be exerting a force on object A. They will be of equal magnitude, but they will be in opposite direction. Here's another example of a girl here in a swimming pool, right? She wants to accelerate herself. She wants to move in this direction. So what does she do to decide to move in this direction? It's difficult for her to just simply start moving in this direction, maybe at a higher speed or whatever she wants. What she decides to do is that I am going to what? Put my feet against the what? The wall of the pool, right? So she's going to exert a force. So her feet will exert a force on the wall. So simultaneously, at the same time as her feet are exerting a force on the wall will be exerting a force on her feet. This is the force that is going to do what? Push the girl to accelerate in the direction she wants to accelerate. So I think with this knowledge of Newton's third law, we can do a lot of things. Think about it. Say you are in a pool of water, right? In a small boat, for example, right? Here you are in a pool of water in a small boat. You want to move in this direction, right? What can you do? If you can get an object that is going to push, let's say maybe here is where the water starts. As long as you can push yourself against this wall where the water starts, then the wall will then be able to do what? To push you in the opposite direction. Then you can move. So that's Newton's third law in application right there and then. So Newton's third law allows us to be able to what? To push ourselves in different direction by applying a force on object A, knowing exactly that object A will do what? Will apply a force back on us. Okay. Again, if we continue with the same examples, right, to avoid again misconceptions grade 12, I want us to remember that these action-reaction pairs, or know that these action-reaction pairs that we are talking about do not cancel each other, right? Why am I talking about do not cancel each other? If you remember last week, we drew free body diagrams, right? And if you are looking at these action-reaction forces, they look like the forces acting on a book like this. If you remember last week, we drew forces, free body diagram, draw the forces acting on the book itself. you would say there's a normal force and the force of gravity, right? These are the two forces that are acting on this book here, right? A lot of you would think that these two forces are action-reaction pairs. This is not true, grade 12 learner. These two forces are not action-reaction pairs because these two forces can cancel each other. These two forces are acting on one object. When we talk action-reaction pairs, they always act on two objects. So they always act on two objects. It's object A exerting a force on object B. Then object B also exerts a force on object A. Those two forces cannot cancel. Forces that can cancel or balance each other are forces on one object, like these ones, the normal force and the force of gravity. So if I say, get me the action-reaction pairs on the book, you cannot say it's the normal force and the force of gravity. No, right? Because for us to have action-reaction pairs, we have to consider two objects. And when you write these ones, you are only looking at one object, the book itself. These two forces are the forces that are only acting on the book itself. But when we want action-reaction pairs, we have to consider two objects, right? The object A that actually exerts a force and the object B that reacts to the force, right? So when you do normal force, if you do normal force here, normal force is caused by the table, right? But force of gravity is not caused by the table or is not even acting on the table. So it cannot be a reaction force, right? So when we talk of reaction forces or action-reaction pairs, they must be coming from two objects. One object brings a force, the other object brings a force. They are equal, they are in opposite direction. Similar to this one, these two forces cannot cancel each other. They are not going to cancel each other because these forces are coming from two objects. I think this is going to be making more sense than this one. If you look at this, there's a force exerted by the person on the chair. And then the reaction force is a force exerted by the chair on the person. Two objects. Person on the chair on the person. Two objects. They cannot cancel each other. Here, the same thing here. We have table on the book on the table. If we want to consider the force of gravity, we would say force of gravity on the book and then book on the earth. Because if you remember, the force of gravity is the force that is exerted by the earth on an object. So if I wanted to see the reaction force of the normal force, I would call the normal force, it is the force exerted by table on the book. So book by table. Are we together? So this is the force exerted on the book by the table. Its reaction force will face in the direction like this. It will be table by book. It will not be the force of gravity. We need two objects. I'm talking the book and the table. Here I'm also talking the book and the table. If I wanted to look at the force of gravity and its reaction pairs, I would say it is the force that is exerted on the book by the earth. The force exerted on the book by the earth. The reaction there will be the force exerted on earth by the book. Newton's third law tells us that if the earth pulls us, we also pull the earth. Because as Newton tells us that when object A exerts a force on object B will simultaneously exert an oppositely directed force of equal magnitude on object A. It doesn't matter the size of the two objects. That's why we can even say when the earth pulls us down, we also pull the earth with the same amount of force that the earth pulls us with. The force is the same, it is just in opposite direction. This is similar to what is happening here again. The two objects here, one are the feet on the wall and the others is the wall on the feet. Two objects. When we have two objects exerting forces on each other, those two forces cannot cancel. The only forces that can cancel or balance each other are the forces that are only acting on one object. So I repeat, action-reaction pairs do not cancel each other. Normal force and force of gravity on an object are not action-reaction pairs. Right, okay. So, if you've been following so far, you're probably confused, right? Because now you have a question to say. If you are saying that the earth pulls me down, I also pull the earth up, then how come when I'm falling, I'm the only one that is moving? I hope you have that question, grade 12. I hope you're also asking yourself to say, how come I'm the only one moving towards the earth, yet the earth is not moving towards me? Right. So we'll try and explain as to what that does not mean. When you are falling, you are no longer pulling the earth. You are still pulling the earth according to Newton's third law. And you are pulling the earth with the same amount of force that the earth is pulling you down, as we are trying to show it here. Right? There is the force, there's the weight, that's the force exerted by the earth on you. And R here is the force exerted by you on the earth. So both of you of yourselves are pulling each other, you and the earth. You pull each other with the same amount of force. Yet, if you are on the air like this, you'll be the only one that goes to the surface of the earth. You'll be the only one that falls. And maybe the question that you would ask yourself is, how come? Why does this happen? Right? I would like to try and explain this to you, grade 12, right? So that you understand, so that we try to minimize confusions on this Newton's third law of motion. Right, we have to go back to Newton's second law of motion from last week, right? To say when we said Newton's second law of motion, we said when an object or when a net force is applied to an object of mass m, it accelerates the object in the direction of the net force. But then the part that was important, we said the acceleration is directly proportional to the net force and inversely proportional to the mass of the object. So what does that tell us? That helps us understand why you are the only one that falls towards the earth. The reason why, as much as you are pulling the earth, the reason why the earth cannot move towards you up in the direction where you are pulling it is because of its mass. If you remember, we said last week, F net is inversely proportional to the mass. And we said F net, mass, not mass and acceleration. F net is directly proportional to acceleration. So F net, not F net, but acceleration, sorry, is inversely proportional to the mass. So that means that if the mass is big, the acceleration will be less. We talked about that last week. We said if the mass is big, the acceleration will be less, right? So when you look at the mass of the earth compared to your mass, right? The mass of the earth is relatively big or very, very big, right? So as much as you are exerting the same force that the earth is exerting on you, the earth will accelerate so small that it is insignificant. We can even neglect it. So the acceleration of the earth will be so small that it can never be seen. We can't see the earth accelerating towards us. It's because of the mass of the earth. It's because of how big the earth is. But the truth of the matter is, according to Newton's third law, we are pulling the earth. It's just that it is so big that it's not going to move. Let's take an example just to try and make you understand. You can try and push a truck, a stationary truck, a truck that is not moving, right? Now, just because, and when you push the truck, it's not going to move. I hope all of us understand and agree here. The truck is not going to move. You don't have enough force to push a truck such that the truck moves. It's not going to move. But just because the truck is not moving, that does not mean you are not pushing. So the force you are exerting on the truck, but the truck is not moving. So a similar thing is happening here. Just because the earth is not accelerating towards us, that does not mean we are not pulling. We are pulling. It's just that the earth has a greater mass. The mass is so big that it cannot, or it will accelerate so small that we cannot even see its acceleration towards us. As compared to the earth, we are so small that when the earth pulls us, we are so small that we will accelerate so quickly and will reach the surface of the earth and will hurt ourselves if maybe we decided to jump off a building. Advise that people must not do that at all. So we are trying to explain the reason why you would find that you are pulling the earth and the earth is pulling you, and Newton's third law tells us that you are both pulling each other with the same amount of force, yet the one is moving and the other one is not moving. I hope this also gives clarity as to why things move, because once we talk of Newton's third law, people start thinking, well, how are things moving then, right? The two properties that we have spoken about, the forces do not cancel each other, right? Things move based on the forces that act on them individually. That's how things move. Newton's second law, right? Okay, and then number two, things move based on the net force that is acting on them and also the mass that is acting on them. So we need to understand and try to minimize confusions based on that. Newton's third law tells us that when object A exerts a force on object B will simultaneously exert an oppositely directed force of equal magnitude on object A. They are going to be the same, they are going to be opposite. It does not matter the size of the object. All we need to be able to do is identify those action-reaction pairs. In this case, the action would be what? The force exerted by the earth on yourself, and the reaction would be what? The force exerted by yourself on the earth. It would be equal in magnitude. It would be opposite in direction. Right. I hope Newton's third law makes sense. It is mostly a conceptual law. It's a law that we need to understand. As much as the calculations are there, but we don't do it in technical science. We don't do the calculations in technical science for Newton's third law of motion. So all we need to know is understand it. Number one, we should be able to state it. We must be able to state Newton's second law, the third law of motion. And then from there, we should be able to identify action-reaction pairs. All action-reaction pairs that we can identify. And then from there, we should know the properties. Right. Okay. So, where does this Newton's third law apply in real life? Because you want to ask yourself, like, Newton's second law applies almost everywhere. Newton's first law, last week we talked about the seat belt, how they make it safer in our cars. Right. So, what about this Newton's third law? Right. So, it is said that rockets are working mostly based on Newton's third law. So how does the rocket pushes itself up? How does the rocket get propelled to go up, right? What happens is that the rocket will release a hot gas, right? Release a hot gas, and what this gas will do, it will exert a force, right? So when it pushes, the hot gas pushes down, it exerts a force. So since it's object A exerting a force on object B, to exert a force on the ground and also on the atmosphere itself. Since that's happening, it's object A exerting a force on object B. According to Newton's third law, object B must also exert a force of equal magnitude. So that's where the rocket will get the force that will push it up. So it's similar to the guy pushing against the wall. So this force that comes from this engine of the rocket, right, in the form of hot gas, right, will act as a force on the ground or wherever the rocket is stationed. As it pushes down, it will then push, or the ground will then push the rocket upwards, making sure that the rocket is accelerating, right? To understand this, I want you to think of a balloon, right? If you take a balloon, right, and you inflate it, okay, but then you decide not to tie it up here, okay, you don't tie the balloon up, but you let it go. What does the balloon do? It starts moving in all different directions. What causes the balloon to move? The balloon releases all the gas that you use to inflate it. So as it releases the gas to the atmosphere, it is exerting a force on the atmosphere. Then that atmosphere will then come up with a what? A reaction force, right? Pushing the balloon in the opposite direction. That's exactly what is happening with the rocket here. As it releases these hot air gas, raises it down, and then the reaction comes in the form of from the atmosphere, pushing the rocket up. Right. Also, the engines of an aeroplane works in a similar manner, right? You have the push of the engine on the gases, pushing them up outwards. as it pushes them outwards, they are also going to react, or the atmosphere will react with a reaction pair, pushing the engine in the opposite direction, allowing the plane to take off. So these are some of the examples where you would find a Newton's third law of motion in our real life, right? Okay, so just to try and sum up Newton's third law, grade 12, before I move on to momentum, right? I want us to look at a summed up properties of action-reaction pairs. In Newton's third law, you must always remember this, I can't stress it enough, that the forces are always equal, but they are in opposite direction. Number two, they always occur simultaneously at the same time. You're not going to have a force acting and another force reacting after some time. They act and react exactly at the same time. They always act in pairs. So you're always going to have two action and a reaction force. Action force, reaction force. As long as it is an action force, there will be a reaction force. Action force, another reaction force. They will always come in what? In pairs. Action, reaction. Action, reaction. Action, reaction. Always. They are always in pairs. They are always equal. They always act simultaneously at the same time, and they are opposite in their direction. Very important. Forces act on different objects. These forces are coming from a different object. This maybe will be object A, this will be object B. This will be object A, this will be object B. If this is object A, this becomes object B. Always they are acting from different objects. Therefore, these forces cannot cancel each other. They are coming from different. The forces that can only cancel each other are forces that are acting on the same object. Forces that we can represent using a free body or a force diagram. But these ones as action-reaction pairs are not from the same object. They are coming from different objects, two different objects. They cannot cancel each other. Again, this is the point we are trying to make. These forces do not balance each other. The forces of action-reaction pairs, they do not balance each other. And the reason is because they are acting from different objects. Right. Okay, that was it for our Newton's third law of motion, and I hope people understand Newton's third law of motion. I hope from here you study it and be able to state Newton's third law of motion and be able to explain and also identify action-reaction pairs, grade 12. Right, now I want us to go into introduction of momentum. Okay, in momentum, I also want us to be able to define momentum, right? So definitions and stating of laws are very, very important. These are things that you cannot forget. These are things that you cannot get wrong when you're writing your exam. You must be able to define. These are things that you know they are going to be there. Know all definitions and know all the laws, right? So you must know this definition as well. And we define momentum as the product of an object's mass and its velocity. The product of an object's mass and its velocity. It is defined exactly like this in your examination guideline. Again, use that examination guideline for definition. Let it guide you for definition and stating of law. It actually guides with everything that you need to know for the year. Okay, so grade 12, we must know that momentum is a vector quantity or a vector physical quantity. What do we mean by a vector physical quantity? I hope you all remember that a vector is a physical quantity that has magnitude and direction. So you have both magnitude and direction. So when we talk momentum, we say momentum is a vector, and it is a vector because it has magnitude and direction. What gives the momentum its direction? Momentum becomes a vector because of what? Of the velocity in momentum. Because we said it is the product of an object's mass and its velocity. Now, because of the velocity then makes momentum to become a what? A vector quantity, because it gives it the direction. Right. So momentum then becomes a vector physical quantity. It has magnitude and the what? And the direction. Okay. Now, mathematically, momentum is represented by the formula P is equals to mv. You'd remember that at the beginning of the lesson, I did identify this formula as the formula that we are going to be working on today, right? So it is given by P is equals to mv, where m stands for the what? For the mass of the object, the product of an object's mass and its velocity, and v represents the what? The velocity. The mass in SI units is measured in kilogram, while the velocity is measured in meters per second, right? So then what is the SI unit of momentum? Becomes extremely simple. We are multiplying the kilograms and the meters per second. Therefore, the SI unit must become what? Kilograms meters per second. The SI unit of momentum. So P there, small letter P, then represents what? It represents momentum. Momentum is measured in the SI unit, kilograms meters per second. So by looking at the definition of momentum, right, and looking at the mathematical representation of momentum, it tells us that momentum depends on two things. What are these two things? It depends on the mass of the object and it depends on the velocity of the object. Okay, so that would be the formal explanation of what momentum is. But maybe after I've explained it like this, maybe you still don't understand. What are we talking about, right? So I'll make example, right? An example and try to make you understand what momentum is. I usually say to simply understand momentum in an informal manner, maybe if I put it like that, I think of momentum as how difficult it is to stop an object that is moving, right? That's how I think of momentum. How difficult it is to stop an object that is moving, right? So there are two things that can make an object to be difficult to stop. Okay, think about it, right? If the object is big, the object has large mass, and like a rock like this, and it's rolling down the mountain, right? An object is going to be extremely difficult to stop, right? Okay, if we compare it to just a tennis ball, for example, if you roll the tennis ball down the mountain, even if they can have the same speed, right? Rolling a tennis ball and rolling a huge rock down the mountain, that huge rock, if you are here and you are trying to stop it, this rock is going to kill you maybe altogether, right? And the reason for that is because the rock has a greater momentum. What's giving the rock a greater momentum compared to the tennis ball if they have the same velocity? The mass of the rock, because the rock has a greater mass. Its greater mass then gives it what? Give it its greater momentum. Okay, but then we can take maybe a big rock again, okay, then take a big rock and then push it in a horizontal surface here, okay, push it in a horizontal surface. Now, because we are pushing it horizontally and we're not rolling it down, the velocity that this big rock will get to is relatively small. Now, if you compare this to a bullet coming from the gun, now, right, look at their masses. The rock is big, okay, and the bullet is very small, be measured in grams, maybe, right? Bullet is very, very small. Now, if this bullet comes to you, the bullet is going to be more difficult to stop as compared to the what? To the rock. What causes the bullet to be difficult to stop as compared to the rock? In this case, it is what? It is the velocity with which the bullet is moving. The bullet moves with a very, very high velocity. So again, as I'm saying, to me, to make myself understand momentum, I always think of how difficult it is to stop something that is moving. If that thing is more difficult to stop, right, then I know that thing must have a higher momentum. But if it's not that difficult to stop, then it must have what? A smaller momentum. Because I know momentum depends on what? On the mass and the velocity, right? So if something is small but has high velocity, it will have high momentum. But if something that is big, right, okay, and then also have maybe high velocity, it's going to have high momentum as well. So momentum depends on two things. It will be the mass of the object and the velocity of the object. Okay, now back to the direction of the momentum. Okay, now I'm going towards calculations. Okay, when I say momentum is a vector physical quantity, this is extremely important grade 12 when we do calculations. We must never forget that momentum is a vector quantity when we go for calculations, because every time that we are going to go for calculation, we must always choose the direction, right, where we are going to say this is our positive direction, so that then the opposite direction becomes negative, so that we'll be able to assign the signs when we are doing the mathematical calculations. So it becomes very important to remember that momentum is a what? Is a vector. This becomes extremely important grade 12. As you are about to see, when I try to do these calculations, the issue of directions becomes important. Okay, right. So let's look at example 1. Okay, example 1 says determine and compare the momentum of a 2,000 kilogram car moving east with a velocity of 16 meters per second and a 5,000 kilogram truck going with the same velocity in the same direction. So we want to compare the momentum of the two cars. Now, before I do any calculation in momentum, as I said, I must remind myself momentum is a vector quantity, so I must always choose direction. So they have been told in the question that the car is moving east. The car is moving east. So I can decide this direction. Take east as positive, or I can take east or west as positive. Are we together? The issue of direction when it comes to momentum is very simple. However, here's what I prefer. Because everyone does maths at school, everyone has been doing maths from lower grades. Everyone knows the Cartesian plane. So what I always advise people to do is they must always assign direction based on the Cartesian plane. Whatever faces in this direction, which is to the right, must be positive, because we know in the Cartesian plane we have positive numbers in this direction. Whatever faces in this direction, which is west or to the left, must always be assigned negative, because we know in the Cartesian plane we have negative numbers in the direction. Whatever faces up must always be assigned positive, because as we go up, it's positive in the Cartesian plane, and whatever points downwards must always be assigned negative, as we know. So this would be an advice coming from me to you. It makes it simple. It makes it eliminates this stressing thing of how should I assign direction. You just look at where it's facing. If it faces to the left, it must be assigned negative. If it goes right, it must be assigned positive. That would be an advice. I have to repeat that it is only an advice. Choosing direction is entirely up to you. Okay, so I will continue with how I assign my direction. So I will say take east as positive. Then I will underline that. I'm telling anyone who's going to look at my calculation that in this calculation, the vectors that are pointing east, I will be assigned a positive value, right? And the vectors that are pointing west will be assigned a negative value. So I have to take direction first, then I can attempt the calculation. And I attempt the calculation by doing what? Writing the formula as it is, taking it from the data sheet, table 2 of the formula sheet there. If you remember, I page through, I go there, I look for the momentum formula, because they said I must determine and compare the momentum. And I'll find that the momentum formula is what? P is equals to mv. This is a skill, grade 12. It is a skill to be able to go, take the formula and use the formula. Being able to choose the correct formula is a skill. And it's a skill that must not be taken for granted. It's a skill that must be practiced over and over again. Being able to identify the formula that I must use and taking the formula and copying it exactly as it appears in the data sheet. That's a very important skill, and that skill must be taken seriously. Right, P is equals to mv. I've taken my formula. This is going to be equals to m. What is the m? The m is the 2000 kilograms times the velocity. What is the velocity? The velocity is 16 meters per second, but the 16 meters per second is facing east. Therefore, I'll assign it a what? A positive. Then I go to my calculator. I do 2000 multiplied by 16. Quickly get the answer. I will get that the momentum is 32,000 kilograms meters per second, and the direction is east. I found my answer to be positive, so it must be going east. And I quickly go and determine that of a truck. They said the truck has a mass of 5,000, right? Because the truck is going same direction, we're still within the same scenario, I can still use this direction that was taken here. Take east as positive. Take east as positive. Then I underline. Then I write P is equals to mv from the formula sheet. What is my mass? My mass is 5,000 now. And the velocity they said is the same, and it's also in the same direction. So it's still going to be what? 16. Then I put that in the calculator. 5,000 multiplied by 16. What do I get? I get 80,000. I get 80,000 kilograms meters per second east. Okay, so that's how we do calculations where we are calculating momentum. But again, with these calculations, I wanted to show you that if we have objects that are moving with the same speed, right, momentum can be affected by the masses of that object. As you see, the truck has a higher mass, so it ends up having a what? A higher momentum. The car has a smaller mass, it ends up having a smaller momentum. Their velocity is the same, to show you that momentum depends also on the mass. Okay, here's example 2 there for momentum. Now they say determine and compare the momentum of a 780 kilogram Formula 1 car going east with a velocity of 378 kilometers per hour and a 500 kilogram truck going with the velocity of 16 meters per second in the same direction. So we're still working with that truck, which is 5,000, going in the same velocity of 16 meters per second. But now we have a different car, right? That is small in mass, okay, but also have a what? A very, very high speed there at 378 kilometers per hour. It's a Formula 1 car that is we are talking about. So we are going to take our direction, take east as positive. I am not allowed to do any momentum calculation without taking direction, great off. I must always take direction. Right, then I write my formula. I will start with what? With the truck. P is equals, because it's the easiest, P is equals to mv, and I've done it before. So it will be 5,000 times 16, and we've done and we found that it was 80,000 kilograms meters per second east. Always indicate the direction. Okay, now I need to do the Formula 1 car. It's also going east, so we are going to say take east as positive. You repeat it as much as necessary. You cannot say I've been writing it over and over again. You must repeat it as much as necessary. This is practice for you. And when it goes to you, it becomes second nature. You never forget it. So P is equals to mv, right? And then our m is 798. However, you would notice that our velocity is 378 kilometers per hour, which is another skill coming from lower grades. You must be able to convert kilometers per hour to meters per second. So how do we do that? Simply take 378 times 10 to the power 3. That's when you are converting from kilometers to meters, times 10 to the power 3, or multiply by 1,000, over 3,600. What's the 3,600? Those are the amount of seconds in an hour, because we are converting from an hour to a second. Kilometer to meter, hour to seconds. So then that's what we do. We say 378 times 10 to the power of 3 all over 3,600. This is another scheme, and not 378, not 377, 378, right? We get that our velocity is 105 meters per second east, right? Okay, there's a shortcut to this grade 12, and I will also show you this shortcut. Instead of going through all of this thing here and you are not interested to that, you can just simply take the number as it is, 378, and divide by 3.6. It's a mathematical shortcut. So you simply say 378 over 3.6. If you do that with me, you will realize that the number is the same, 105. So you choose the one you are most comfortable with. And I think that most people will be most comfortable with this one. It's a mathematical shortcut, and if you want to use it, please do so. Right. Now, so the velocity that we are going to substitute here is 105. Question, why are we not substituting the 378? Why not? Remember, we work in SI unit. We work in SI unit, and all numbers that we substitute must be in SI unit. Hence, kilometers per hour is not the SI unit. It's a unit, but not SI. SI is meters per second. So we must always convert back to SI unit, and we work in SI unit. Grade 12. So let's do the calculation. 798 multiplied by 105. We get that the momentum here now is 83,790 kilograms meters per second east. As you can see, again, the momentum becomes greater. This momentum becomes greater. And what makes this momentum to be greater? It is the velocity. The velocity here was only 16, and the velocity here was 105 meters per second. I hope the issue of calculating momentum is becoming clear to you, and it becomes easy. And I hope you understand the issues of taking direction every time you have to calculate momentum, grade 12 learning. And I hope you do not forget these things, because they are extremely, extremely important. Right, so that's momentum. The product of an object's mass and its velocity. P is equals to mv, where m is the mass in kilograms, the velocity, v is the velocity in meters per second. The SI unit becoming kilograms meters per second, because we are multiplying the mass and the velocity. Okay, so what else can we say about momentum? We can say momentum can change. Momentum of an object can change, right? What can change the momentum of an object? Well, there are two things that can change the momentum of the object. Those are the two things that the momentum depends on. What are those things? It's the mass of an object that can change the momentum of an object. And it's also the what? The velocity. So the mass of an object, changing the mass of an object can change the momentum of an object, right? And then changing the velocity of an object can change the momentum of an object. But let's think about it. Think about yourself, maybe running. If you run and then you increase your speed, your velocity, your momentum is going to change, right? But what are the odds of your mass changing within the same run? They are highly unlikely, right? It is highly unlikely that the mass of the object will change to cause the change in the momentum, right? So with that being said, when we look at the change in momentum, right, for our scope, grade 12 technical science, we are only going to be looking at the what? At the change in velocity. We're not going to consider the change in momentum. Not to say that the change in mass, not to say that the change in mass does not change the momentum, but we are saying that it is highly unlikely that within the same movement, the mass of the object changes. It is highly unlikely. Most of the time, what will change is the velocity of that particular object. Now, with that being said, for change in momentum, we can just focus on what? On how the velocity is what? Is changing. So the factor that we are going to look at most of the time, that is going to be changing, not most of the time, all of the time, that is going to be changing our velocity for this year, is our momentum for this year, is only the velocity. So only the velocity will change the momentum. Okay? So I'm saying that momentum can change, and what can change the momentum? It's either the mass or the velocity. However, because it's highly unlikely to change the mass of an object, it's going to be the velocity that is going to be changing our momentum going forward. All right. So change in momentum can also be calculated. So we should be able to calculate how the momentum of an object changes. Think about it. Right? So change in momentum is calculated by this formula, or given by this formula, delta P, right? This delta P represents the what? The change in momentum. How the momentum changes, right? Given by the final momentum, okay, the momentum after there has been a change in the velocity, okay, minus the initial momentum. So if you say delta P is equals to PF minus PI, that's change in momentum, right? Now, if you remember that momentum is equals to M times V, mv, then I can work out this formula a little bit further, try to solve it or try to expand it, right? I can say, instead of writing a PF minus PI, right, I could write it as delta P is equals to M times VF, the final velocity, the velocity that is changing. So I could actually start it here. Delta P is equals to M delta V. This delta represents the change. I just said to you a moment ago, what is going to be changing for us, or the variable that we'll be looking at, is the change in velocity. Therefore, change in momentum for us would be M delta V, the change in velocity, how the velocity is changing. Now, if you remember from grade 10 again, change in velocity we represented as Vf minus Vi in grade 10 when we're doing that acceleration. We also did it even last week. Change in velocity is given by Vf minus Vi. So if that is the case, instead of writing it as Pf minus Pi, I could write this formula as delta P is equals to M delta V, change in velocity. That's the thing that will change, that will cause the momentum to change, if you remember. Right. Delta P then could be written as, instead of now writing it as delta V, I could write it as mvf using this formula, because momentum is actually mv. So it will be mvf, that's m with the final velocity, minus mvi, that's m the mass with the initial velocity. Right. And then mathematically, I could just simply see that I have m as a common factor here. Then I will have delta P, take out m as a common factor, and I'll be left with Vf minus Vi, right? Why do I have to go through all of this? It's important that I show you all these formulas, grade 12, because we don't know which one we will need when. We might have to use this one, especially between these two. We might have to use this one depending on what the question requires, and we might find ourselves having to use this one, right? This one and this one are one and the same thing, right? This one here and this one. It's just a mess has been taken out as a common factor there. So we might find ourselves having to use this one, we might find ourselves having to use this one. So we need to know. It must not be a matter of memorizing that the formula will always look like this. We must know that the formula comes from here and it goes all the way up to here. Because it might happen that we find ourselves having calculated the initial momentum, having calculated the final momentum. Now we are asked the change in momentum. So if that is the case, we simply do what? Use this one on top here. But if maybe we are given the velocity of the object and the mass, then we might find ourselves having to use this one. So both are equally important. Right. The SI unit for change in momentum is still kilograms meters per second, because we're still talking about what? Momentum. And if we're still talking about momentum, we have to say again, direction is still important. It's still very important. The direction is extremely important. So whether we're calculating momentum or the change in momentum, we still have momentum there. So direction becomes extremely important. Right, let's look at examples and see how maybe can we use the formulas to calculate change in momentum. Right, so example 3 here says to us, a car with a mass of 1000 kilograms is traveling at 72 kilometers per hour. When the driver sees a dog running across the street, right, 72 kilometers per hour, 1200 kilograms, just highlighting my given there, and sees a dog running across the street, he applies the brakes, and 10 seconds later, the car is moving at 18 kilometers per hour, right? I also have 10 seconds later here. Okay, question number 1, calculate the initial momentum of the car. They only want the momentum, and I've done the momentum before. But what do I do first? I must always take direction. In this case, I am not given direction where they say to the right or to the left. So how do I determine direction in that case? Well, I just say direction of motion is positive, right? Wherever the object may be going, be it to the right or to the left. But that direction of motion, I'll take it as positive. So that means to me, the opposite will have to be negative. It has to be. Okay, so I'm calculating the initial momentum. The initial momentum should be given by the formula P is equals to mv, because it's simply momentum. All right, so the m of the car is 1200. The velocity of the car, if you see again the velocity that is given as what? As 72 kilometers per hour. So I have to convert it and say 72 divided by 3.6. I'm doing that one that takes a shortcut, right? I want to take a shortcut. It's the easiest. 3.6, right? I will find that this is 20 meters per second. So here for velocity, I will substitute 20 meters per second. And remember, grade 12, if you have to do conversions, they must be shown wherever you are working. Your working must always be shown. You cannot come with 20 that we do not know where it comes from. You must show us that you understand where the 20 meters per second comes from. It's a skill. It's a skill being able to convert. So I want to see you showing me that skill. It cannot just come from thin air. I will find that my momentum is 24,000 kilograms meters per second in the direction of motion. In the direction of motion, right? Right. Number 2, calculate the final momentum of the car. The final momentum of the car is when the car is now moving at 18 kilometers per hour. Okay, so again, I have to take direction of motion as positive and underline every time you take the direction. So I'm going to say P is equals to mv, where m is equals to 1200 again, because we're still talking about the same car. Now we have to go and convert the speed or the velocity of the car, right? So we have to do 18 over 3.6. 18 over 3.6. We find that it is 5 meters per second. So we multiply by 5 here. And then we get our calculator again, 1200 times 5. What do we get there? We get 6,000 kilograms meters per second. Again, it's in the direction of motion. Always do not forget to indicate the direction. The last question is now then asking us, calculate the change in momentum of the car. The change in momentum of the car, we determine it by saying delta P is equals to PF minus PI in this case. Why? I have already calculated the PI. I've already calculated the what? The PF. So I can simply take these numbers and substitute them. PF is equals to 6,000 minus PI, which is equals to 24,000. So I'm going to do 6,000 minus 24,000. I should get an answer of negative 18,000 kilograms meters per second. Now, grade 12. How then do I represent this number here? This negative. Do I leave it with a negative and say this negative is my direction? The answer to that question is no, grade 12. You cannot leave it with minus and say that's your direction. Remember, negative, it's a mathematical symbol. Negative. Are we together? So we're doing science here, not maths. At the end, we must conclude scientifically. So it means we must give our direction in words. So you cannot leave it with a negative and say you have indicated direction. What you should do is drop the negative because we borrowed it from maths. Now we're coming back to science and write 18,000 kilograms meters per second. Then write your direction in words. So since the positive direction was the direction of motion, the negative direction has to be the opposite direction of motion. So you are going to say opposite direction of motion. That's how you would find your answer in this case. So what I'm trying to show you how to calculate the change in momentum where you already have the initial momentum and the final momentum. So you use delta P is equals to PF minus PI in that case. Okay. But now we have example 4, where again we need to do and calculate the what? The change in momentum. Example 4 says to us a 1 kilogram ball, right, with a velocity of 5 meters per second. So this ball is 1 kilogram, has a velocity of 5 meters per second to the right. They say it goes to the right, collides with the wall. Here it is here, shown in the diagram, colliding with the wall, right? It is moving 5 meters per second. It collides with the wall and bounces back with a velocity of 3 meters per second. So when it bounces back here, it now has a velocity of what? 3 meters per second. And the question is, we should determine the change in momentum of the ball. How did the momentum of the ball change? Okay, now there are two options here, Christoph. You can take a longer option, which is time consuming, but if that's what you're comfortable with, it's better than losing marks. So the option number 1 is to calculate the momentum of the ball before or initial. So we're going to do P is equals to mv and calculate the initial momentum of the ball. So 1 times 5. Then after that, calculate the final velocity, the final momentum of the ball, as we did in the previous question. Then from there, we do delta P is equals to PF minus PI, and then take the answer on top minus the answer at the bottom, or vice versa. And then we get our answer there. Right, we can do that, or we can remember that formula that we're talking about, delta P, that delta P can be expanded to M open bracket VF minus VI, or delta P is equals to MVF minus MVI, right? Personally, I like this one, the one where the M has been what? Taken out as a common factor. So I'm going to stick to it in this example as well and take this one where M is taken out as a what? As a common factor. So, but before I do the calculation, what's the first thing? I must take direction. So you must take direction. Luckily this time around, I have a diagram that shows me a ball going to the right and bounces back to the left. Also, I have a what? I also have it here that 5 meters goes to the right. So I don't have to stress about this direction of motion, opposite direction of motion thing that I had to deal with in the previous example. Here, I can just simply say, take right as positive and underline every time before I attempt a momentum question. or a question that has momentum in it, I need to take direction. I cannot attempt without taking direction because mistakes will be made and answers will be wrong. It's important that we take direction, grade 12. Right, so from there, I then go to my formula sheet, look for the formula. I will find the formula looking like this or looking like this. And then I'll say delta P is equals to mVF minus VI. Take the formula from the formula sheet, a skill again that we were talking about. Then from there, it's simple. We start doing what? Substituting. So you remember, you see, we are avoiding this thing of having to calculate the initial momentum, having to calculate the final momentum, then doing final minus initial at the end. It will take time. I can simply do it like this and save myself a lot of time. So I'm going to say my mass here is 1 kilogram. Okay, what is my velocity? My velocity, finally, it is moving at 3 meters per second. Now, we have to be very careful. Look at 3 meters per second. The 3 meters per second is pointing to the left. However, we said to the right must be positive. So it means anything that points to the left must be negative. Very crucial here. If you make a mistake here, that's when you're going to get it wrong. If you don't take direction here, that's when you might forget and make a mistake here. Just substitute 3 as it is. 3 cannot be substituted as it is here. It must be substituted with a negative value, minus 3, because it is pointing in the opposite direction. We said we're taking right as positive. Minus 3 or negative 3 minus 5 meters per second, which was going in the positive direction. And then from there, we check how the momentum is changing by using the calculator. So we're going to say 1, open a bracket, negative 3 minus 5, close that bracket. We will get that our change in momentum is equals to minus 8 kilograms meters per second. Then again, we ask the question, should I leave it like this with a negative just as my direction? And the answer again to the question is no, I cannot do that. The negative is just a symbol or a sign that is borrowed from maths, right? We just use it when we are doing calculations. But scientifically, we have to conclude using weights. So because the answer is our conclusion, so we have to conclude using weights that it is 8 kilograms meters per second to the left, because we're talking about right here. It's opposite to the right. Né? So our answer should be change in momentum is equals to 8, we are dropping the negative now, kilograms meters per second to the left. That's how you should indicate direction. Direction must always be indicated in words. Direction cannot be indicated using signs and symbols. Okay? What you cannot do as well, you cannot say minus 8 kilograms meters per second and then say left. This again is wrong. Right? You are now indicating direction here. It still has this minus that we do not want, but you're also indicating direction here. Now it looks like it has 2 directions, right? Looks like it has 2 directions. You do not do it like that. You must always drop the negative and write it in words. It shows understanding. It shows that you understand what this negative represents. That's why we need it, or we want it to be what? To be in words. Again, scientifically correct. You must conclude and write it in words. So grade 12, those are the examples that I have for you with change in momentum. So we've done Newton's third law of motion, looked at it, stated it, right? When object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A, right? And then we said let's identify action-reaction pairs there. And then we looked at the properties that they are always equal in opposite direction. They are always acting simultaneously. They act in 2 different objects. They cannot balance each other or cancel each other, right? It's always 2 forces. So remember all those things there, right? And then we looked at momentum, the introduction of momentum as the product of an object's mass and its velocity, written mathematically with the formula P, small letter p, is equals to mv, where m is for the mass in kilograms, v is for the velocity in meters per second. And the SI unit for momentum then becomes kilograms meters per second. We've done examples of how to calculate. We've said momentum is a vector. It is a vector because of velocity. And if momentum is a vector, when we do calculations that are relating to momentum, it is extremely important that we always start by taking direction. It is extremely important that we always start by taking direction so that at the end we'll be able to conclude and get the correct answer. Then from there we said momentum can change because momentum depends on two things. It depends on the mass and the velocity. So if you can change one of those things, then momentum of the object will change. So we can change momentum by changing its mass. We can also change momentum by changing its velocity. However, we know the difficulty of changing the object's mass. So since that is the case, we are going to look at changing in momentum by only changing velocity. That's for the remainder of the year. Our change in momentum will only be changing velocity. So we looked at change in momentum and we said change in momentum is based on how the velocity of an object changes. The object maybe was moving at 5 meters per second, now it's moving at 3 meters per second, as the example is showing here. It tells you that the momentum of that object has done what? Has changed. It can be calculated. It can be calculated using a formula. Delta P is equals to PF, which is final momentum, minus PI, which is initial momentum. Right. And then that formula can be expanded to delta P is equals to M delta V, the change in velocity, right? Further expanded to delta P is equals to MVF minus MVI. If you take the M out as the common factor, delta P is equals to M open bracket VF minus VI. Then we can calculate, making sure that we are always remembering the issue of what? Of direction when we are doing change in momentum. So let's look at some questions here as an activity and try to see if we can answer some of these questions, right? If we understand what we've been talking about this whole time, right? So we'll look at this activity together and we'll try to also answer this activity together and see how far we can go. Right, 2.6 says, a woman and a man are standing facing each other on an icy frictionless surface. They are both on ice skates, right? The man pushes the woman away with his hand with a force of 100 newtons. So they tell us that the man pushes the woman away with his hand with a force of what? Of 100 newtons. And she moves to the right. Now, before we even look at what the question is, what do we expect is going to happen to the man? Because the man pushes the woman and they tell us that the woman moves. Here's the arrow showing us that the woman is going to move to the right. Right? What do we expect that is going to happen to the man? Right? And if you pay attention, it's similar to the wall question that we had at the beginning. The man is also going to move to the right. And what moves the man to the right? When the man pushes, man becomes object A, woman becomes object B. When object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A. So when a man pushes the woman with 100 newtons, the woman will also push the man with the same amount of force, 100 newtons. So we expect that the man should also move to the left while the woman moves to the right, and they separate. Okay, right. So 2.6.1 asks us, how will the magnitude of the force exerted by the woman on the man compare, right, with the magnitude of the force exerted by the man on the woman? How do they compare? Right? Only bigger than, smaller than, or equals to? Right. I hope everyone with me is saying the answer is equals to or equal to. The magnitude of the force exerted by the man on the woman is equal to the magnitude of the force exerted by the woman on the man. Right? Okay. 2.6 or question 2.6.2 asks us to name and state the law that was used to answer question 2.6.1. Even if this question was not there, I was going to ask myself to say, how do you know that it is equals to? Well, we are guided by this law named Newton's third law of motion. We are guided by this law called Newton's third law of motion. This is why, grade 12, it is important that you are able to state this law. Look at the marks that you are now getting just by being able to state the law. You are now getting the mark of stating that it's Newton's third law because they say name and state, and it's in capital letters. Very, very important. Name and state the law. You don't just go and start stating the law. You have to give it a name first. In fact, I always advise people, every time you state a law, write its name down. Whatever law it is, Newton's first law of motion, then state it. Newton's second law of motion, then state it. Let that be your everyday thing. So, you're getting a mark for just simply naming Newton's third law of motion, and then also stating when object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A. 2 marks extra there. Then that becomes what? 1, 2, 3 marks. And just by saying that equals to here, you already have 4 marks. These are 4 simple marks just by understanding Newton's third law of motion. Okay, let's look at another question there. Right, before we look at another question, this is our solution. As we have said, it is equals to, right? And then the law was Newton's third law of motion, and it says when object A exerts a force on object B simultaneously exerts an oppositely directed force of equal magnitude on object A, and you get 2 marks for that. In total, 1, 2, 3, 4 free marks. 4 marks that no one should be missing, grade 12. Everyone should be getting these marks. Right, let's look at another question. Okay, this one here is a calculation question. So they are saying a basketball of mass 90 kilograms is dropped and strikes the floor with an initial velocity of 7 meters per second, right? And it bounces back with a final velocity of 4 meters per second as shown in the diagram below. And they say we must calculate the change in momentum. 3 marks, right? I want these 3 marks to be 3 free marks for you, grade 12. I don't want anyone to get any question wrong when it comes to this momentum thing. This should be free 3 marks. The first thing, identify all the given. We have 90 grams here. We have 7 meters per second as initial velocity. We have 4 meters per second as final velocity. Right? So we've identified that, right? Now, I'm identifying the 90 grams. So that tells me that this 90 grams must be converted because I cannot calculate in any other unit other than SI unit. And the SI unit for mass is what? It's grams. So I must convert this 90 grams. And how do I convert 90 grams? It is 90 times 10 to the power minus 3, or 90 divided by 1,000 for those who divide, right? So 90 times 10 to the power minus 3, or 90 divided by 1,000. You should get that the mass is 0.09 kilograms, right? So now we can do the calculations. Now we have converted that SI unit, or that unit to SI unit. To do the calculation, the first thing we must do what? Take direction. I will take upwards as positive. I will take upwards as positive. Then from there, I write the formula. Delta P is equals to mVF minus VI, where the M as converted is 0.09. The final velocity, the ball starts by going down. Initially, they told us 7. The final velocity is what? Is 4 meters per second, which is going up. So the 4 meters per second is going up, so it should be positive. So that's 4 meters per second minus the initial velocity is 7, which is going down. That should be negative. So minus -7. Then from there, take my calculator, 0.09, open the bracket, then I say 4 minus -7, close the bracket, I get the answer as 0.99 kilograms meters per second. Upwards, because the answer I'm getting is positive. And I said positive is upwards. That becomes my answer. Great off. For the person who's going to take downwards as positive, they should get their answer negative. Right? So then that tells us that if you're getting your answer negative, the change in momentum is upwards. Are we together? Because you've taken downwards as negative. Something that looks like this. There are two options. So here's a person who's taken downwards as positive. You should then ultimately get your answer as a what? As a negative, right? But the change in momentum is still what? Upwards, because you said downwards is positive. Then upward is negative to you, according to what you've changed. If you've done it like myself, you should find just your answer simply as 0.99, which is also what? Upwards. Okay, right. Another example here, where we are calculating the change in momentum. Says a car with a mass of 1.2 times 10 to the power minus 3 kilograms, right, my given them, traveling with a velocity of 15 meters per second to the left. This time around, we are giving direction to the left, so it should be simple. Hits a wall and rebounds to the right with a velocity of what? 2.6 meters per second, right? To do the calculation, simply do what? Start by taking direction. I'm giving left or right, and I always take right as positive. It makes my life simple. I don't want to complicate my life. Then I underline. Okay? And then from there, formula. Delta P is equals to mVF minus VI. Then I substitute the mass, which is 1.2 times 10 to the power of 3. Open bracket. What is the final velocity? The final velocity is what? Is 2.6, which is a rebound to the right. So the final velocity is positive, because I said to the right must be positive. So the final velocity is 2.6. A rebound when the car hits the wall, bounces back with 2.6 to the right, that is positive. Minus the initial velocity of 15 meters per second that was going to what? To the left. So it's minus a negative 15, close the big bracket. Then from there I go to my calculator, 1.2 times 10 to the power of 3. Open the bracket, 2.6 minus a negative 15, close the bracket. I should find that my momentum or change in momentum is 21,120 kilograms meters per second to the right. SI unit with the direction. That is the change in momentum. Again, for a person who takes the opposite direction here, they should find their answer as negative. So for those people who's going to take to the left as positive, they should find their answer as what? As a negative. But that still means that the change in momentum is to the right, as it shows here. All right, so you have two options here. Here's a person here who did it like me, taking to the right as positive. You should get your answer like this. But if you take here as negative, your answer should be negative here, even though in my solution it does not change, but there should be a negative here, which part will still mean to the right, as you have taken that direction. So that is it with our lesson for today, grade 12. We thank you. Hope to see you next time.